All right, morning everyone. Hope you're having a good start to the day. For those who don't know me, my name's Justin Turvey. I'm the General Manager for the Northern region. I'm based up in Brisbane and I've been in the business for about 17 years or something around that point. And yeah, I was just, I suppose my job today is just to MC this this webinar. This is our third so far this year of the webinars that we've been holding for our customers. And today we're going through some of the work that we've done at our long-term trial site at Glenelg down in central New South Wales, Grenfell. And yeah, the main focus is around nitrogen losses and some of the work we've been doing with our enhanced products like green urea and N-Power as well. And going through the data will be Robert Ibrahim as well as Jan Edwards. I'd say that there's still a few people joining there, sorry. I'll just let him in, there we go. Yeah, I'd say green urea, this season in particular has, the interest around green urea in the market has been exponential, really. We've had a record month on green urea sales this month alone, and there's certainly a lot of interest and a lot of demand picking up for it. So it's a really good opportunity this morning to understand some more specifics and some of the trial work that Incitec Pivot puts in to promote these kind of products in the market. I think that's it for me now, so I'll jump back in with the Q&A. There's a Q&A section up the top of the screen there. If you've got any questions, we'll cover those at the back end of the presentation. And without further ado, I'll pass over to our agronomy team. Thank you.
Thanks, Justin. Robert, if you could move to the next slide, please. Good morning, everyone. I'm Jan Edwards. I'm the Director of Agronomy and Sustainability at Incitec. I'm based in Toowoomba. My co-presenter is Robert Ibrahim, who's the research agronomist and, importantly, the lead scientist on this trial series that we've been putting together on nitrogen losses. I also want to acknowledge the other two key members of the team for this trial program, and they are Clint Sheether, who's our former technical agronomist at Young. Clint set up this particular component of the trial, constructed all of the measuring tubes and did all the hard work of taking all the measurements, the regular measurements for the trial site. And without him, we wouldn't have this data set. And the other person to acknowledge is Jim Laycock, who's our now retired senior technical agronomist, who set up the long-term trial site at Grenfell in 2007 and managed it through to its closure last year. So Jim helped design the nitrogen loss component of this and was on hand for some of the sampling. So a very big thank you to both of those people for their work in this trial. Also, what's really important is I want to acknowledge a few more people. First and foremost is our site cooperators, Duncan Lander and David Partridge, without whom this trial wouldn't have been possible. Not just this nitrogen component, but the broader long-term site at Grenfell. It is no small thing to have a trial as big as this on your farm. So a very big thank you for their patience and understanding, and also for their commitment to R&D. Secondly, to Calix for their ongoing management of the site over a number of years. And finally, to the Incitec Pivot team, of Bilal, El, Fiona and Bede, who helped set the trial up and also helped with a lot of the sampling. Right, without further ado, so the trial we're talking about is located on a property near Grenfell, so 19 k's from Grenfell, about 41 from Forbes. As I said, it is situated on our long-term nitrogen by phosphorus trial, which was set up in 2007. Essentially, for that trial, the setup of the trial is that each plot that we're going to be talking about gets phosphorus banded with the seed. Then 50% of the nitrogen is applied at planting, placed sort of 5 centimetres directly below the seed, and the balance goes on at top dress. Couple of things also to note about the site. Firstly, that this site has a phosphorus coal well prior to this trial going down this last year of about 50 milligrams per kilogram of coal well P. It also had soil nitrate levels around the 53 as well. Nothing. I don't think there's anything else particularly there. So, Robert, if you wouldn't mind moving to the next slide, which is yours, and I'll come back in later. Thank you.
Sure. Thank you, Jan, and thank you for the information and the background. I'll be taking you through the trial results, but before that, let's take a quick look at the nitrogen cycle again. So I know this is a reminder, as most of you have seen this before. So in terms of urea, once you apply urea, it undergoes hydrolysis to form ammonium and carbon dioxide. So just think about it this way. In the absence of urease enzyme, the urea is very stable, even in the presence of water. So it takes years for it to undergo that complete hydrolysis. But once you throw in the urease enzyme, which is everywhere in the soil, this process is pretty fast. So the formation of ammonium makes it that you have a high pH around the granules and makes the ammonium susceptible to volatilization as ammonia. Now, whatever ammonium is left in the system is later biologically converted to oxidized forms of nitrogen. So you're talking about nitrite and nitrate, and they both have negative charges. So because of their negative charges, they are very mobile in the soil. And because they are very mobile in the soil, they can be lost through leaching under high rainfall or high soil moisture conditions. And again, under high soil moisture conditions, this nitrate can be denitrified to nitrous oxide or N2O. And under extreme soil moisture conditions, it can further be denitrified to dinitrogen or N2. So once you apply urea, in this case, it's very susceptible to various forms of losses. For ammonia, for instance, you can lose up to 30% of your applied nitrogen. And for nitrous oxide, it's usually low, around 1.8% in high soil moisture conditions, or a little bit lower than that. So what are the solutions? So IPF has two distinct products to address this loss pathways. The first one is green urea, and as you see, it's urease inhibitor. So what it does is to slow down the activities of the urease enzyme. And by so doing, the accumulation of ammonium is reduced. And then the losses are also cut down. So in certain trials, you're able to see more than 80% reduction in volatilization losses once green urea is used instead of untreated urea. For denitrification losses, we have N-power treated urea. So this is nitrification inhibitor. It slows down the activities of the ammonium oxidizing bacteria. So in slowing down the activities, there's less substrate accumulation. So here I'm talking about nitrates, and there's less losses in terms of nitrous oxide leaching, nitrate leaching, and also dinitrogen. Before I take you to the results, I'll take you through the treatments, parameters, or some variables. So we have two trials happening concurrently at the same site. So the site is planted with wheat. So for nitrous oxide, we compared two products, urea, untreated urea, and N-power treated urea. So these products were applied at sowing, so sometime in May. So we applied them with the seed, so they were bundled with the seed. And for the purposes of this trial, at 3 rates, so 0, 60, and 120 kilogram nitrogen per hectare. And those sites also received 20 kilograms per hectare phosphorus. The machines of interest here is we're measuring nitrous oxide, and the measurements were from the time of fertilizer application or time of sowing for a period of 120 days. We had 3 replications for each of the treatments in a randomized complete block design. Now, when you come to the ammonia, same in wheat trial, we're comparing two products. We were looking at untreated urea and then looking at green urea, and they were applied as top dress in August. So here we're looking at 5 different nitrogen rates: 0, 15, 30, 45, and 60. So this is the second half of the application, because as sowing, we only applied half of the required nitrogen rate. So the top dress came in to supply the remaining half of the required nitrogen. So here we're measuring ammonia, and then the measurements were for a period of 16 days, because this is when nitrogen or urea is very susceptible to volatilization losses. We had 4 replications for each of the treatments in a randomized complete block design. I'll show some of the key activities and when they occurred. So just some timelines. So the sowing was in May 2024. And as sowing, that's when we applied the NPAR treated urea or just untreated urea. And the purpose is to measure nitrous oxide emissions. So the chambers, the greenhouse chambers, which I'll be taking you through later on, were installed at sowing. And then the measurements were for 120 days. About 2.5 months afterwards, we brought in the second half of the nitrogen required, and we used either urea, untreated urea, or green urea. And then we installed the systems to measure ammonia volatilization for 16 days. So the trial went on, and then the harvest was somewhere in November 2024. Now let me show you how the measurements were done. So we had 2 separate systems to measure nitrous oxide emission and ammonia volatilization. For nitrous oxide, we had this static or non-steady state chambers. So what happens is that once you isolate the area, we create an airtight environment. And then we come in from time to time to take gas samples. Because we take the gas samples over a period of time, it allows us to calculate the change in flux or the slope of the emissions. So we draw the headspace gas as illustrated in this image. We use needle and syringe to draw the headspace gas into evacuated vials. And then we send the vials for analysis with GC to quantify the concentration of nitrous oxide in that gas. For ammonia volatilization, what we did was that we used acid-treated foams. So the acid treatment is just to create more hydrogens. So once the ammonia is volatilized and it comes in contact with the acid, it's converted into ammonium, and then we can extract that ammonium, and through flow injection analysis, we can quantify the concentration of ammonium in that extract. So this is how the measurements were done. So the photos are just the PVC pipes with the sampling pot on top for the greenhouse gas or the nitrous oxide measurement. And there for the ammonia, we have the PVC pipe, we have the acid-treated foam suspended in a pipe, and then we just change them from time to time over the measurement period. We have a cap sitting on top of the pipe, and the main purpose is to exclude moisture. So if there's rainfall, we don't want the water washing down the acid to the soil. Now let's look at the results. So I'll start with nitrous oxide. So the graph you see here, the x-axis shows the applied nitrogen rate. So in this case, 0, 60, and 120. The y-axis shows the total nitrogen loss in terms of, or true nitrous oxide in kilogram nitrogen per hectare. The orange bars for urea, the pink bars for NPAR treated urea. The arrows are showing the percentage reduction when NPAR is used instead of untreated urea. So in this case, you see for the 60 kilogram nitrogen rate, we measured 64% reduction in nitrous oxide losses when NPAR was used. And then for the 120 kilogram N per hectare, we measured 73% reduction in nitrous oxide losses relative to using untreated urea. So this is significant loss reduction when NPAR is used. The table is showing the percentage losses and the absolute losses when urea was used compared to N-power treated urea. So for the percentage loss between 0.2 and 0.3% of the applied nitrogen being lost as N2O. And that is equivalent to 0.2 to 0.3 kilogram nitrogen per hectare. For the N-power treated urea, it was approximately 1% of the loss coming as N2O, which is equivalent to 0.06 to 0.07%. Sorry, 0.06, 0.07 kilogram nitrogen per hectare. Now, these losses may seem low, which is actually low in terms of absolute figures. But once you look at the implications of nitrous oxide on the global warming potential or on climate change, this is huge because the nitrous oxide is 273 times energy absorbing capacity. It has 273 times energy absorbing capacity relative to carbon dioxide. So though we are losing just 0.2 to 0.3 kilogram nitrous oxide, in terms of carbon dioxide equivalent, is up to 49 kilogram of carbon dioxide. In other words, you need to emit almost 50 kilograms of carbon dioxide to match the impact that this 0.2 to 0.3 kilogram nitrous oxide is going to create. So the values look small, but their impact on the environment is huge. So this tells you the importance of reducing nitrous oxide emission through the use of N-power, which shows between 64 to 73% reduction. Now let's look at the ammonia. So same format. The x-axis is showing the kilogram nitrogen applied, so 15, 30, 45, and 60. The y-axis is showing the total nitrogen loss through ammonia volatilization in kilogram nitrogen per hectare. The orange bars are for urea, the green bars are for green urea. The arrows are showing the percentage reduction in losses once green urea is used instead of using untreated urea. So for the different rates, you see different reduction. So for the 15 kilogram N per hectare, we observed 48% reduction in losses, then 77% reduction for the 30, 83% reduction for the 40 kilogram N per hectare, and then 53% reduction in losses for the 60 kilogram N per hectare. The table is showing the percentage and absolute losses of nitrogen through ammonia volatilization, comparing urea to green urea. So if you look at the urea, we lost between 20 to 25% of our applied nitrogen, which is very significant. And that is equivalent to between 3 to 15 kilogram nitrogen per hectare. For the green urea, we lost between 4.2 to around 12% of the applied nitrogen, which is equivalent to 1.5 to 7 kilogram nitrogen per hectare. So overall, we observed a significant reduction in emissions once you applied green urea, so between 48 to 83% reduction in emissions. So I'll hand over to Jan, and then I'll come back again to summarize the results.
Thank you. So one of the ways to visualize what Robert is talking about is to run some very basic economic modelling over it. And I guess the key message to think about is that any lost nitrogen can be really expensive. So what we've done with the Grenfell trial data is estimated two things: the cost of both the lost nitrogen in and of itself, and then the lost production from that. So if we look first at the green urea trial, because that's the easiest one to work through, what I've done is looked at the 60 kilogram per hectare top dressing rate and run a basic calculation through looking at the cost of urea per kilo, the nitrogen loss in kilograms of nitrogen per hectare that Robert was talking about, and then worked through what the cost of that lost nitrogen is. And in this particular trial, we measured nitrogen losses of 15 kilos per hectare in the standard urea plots versus 7 in the green urea treated plots. If you calculate that out, that is a loss of $26 a hectare in the standard urea versus 13 in the green urea. If you then calculate through that in terms of a lost production, so kilograms per hectare of wheat yield, and then calculate that through, in the standard urea plots, it was $113 per hectare versus 53 in the green urea. So you can see that lost nitrogen can be very expensive. So overall, you've got a difference there in $73 per hectare from the green urea. So the case at the Grenfell trial site, given the losses experienced there, the case for green urea is quite strong. If we then look at the NPower results from the nitrous oxide trial, it's a very different story. So using the same methodology, if you follow through that economic modelling, because the losses are quite small, despite the fact that the NPower was incredibly effective at reducing the nitrous oxide losses, because those losses on an absolute value in terms of kilograms of nitrogen per hectare were quite small, so 0.22 and 0.12, it follows that the benefits of NPower in this scenario, given that you are investing sort of $11.50 per hectare in inhibitor, are just not there on this particular site. However, if you go to a site where you are prone to these kind of nitrous oxide losses, for example, further north in a cotton crop, and you run similar numbers at the nitrogen application rates and using the loss figures that you would generate in that environment, in a summer environment where it's wetter, then you can clearly see that in a different environment, NPower can be extremely useful and extremely economic in reducing those nitrous oxide losses. So choosing the product for the scenario, for the paddock, for the situation, is incredibly important. In the Grenfell trial, the use of NPower at sowing isn't as economic as it would be in a different scenario. However, the case for green urea on that Grenfell site is quite clear.
Thank you. I'll just take you through the summary of the results. So it's a good reminder that once you apply urea, it's very susceptible to significant losses. So like we mentioned before in the beginning, up to 30% of your nitrogen can be lost. So in this case, we observed on average 23% of the applied urea nitrogen was lost as ammonia, and then 0.24% through nitrous oxide emissions. So this represents significant losses. And yeah, it's important, like Dan just took us through the economic modeling. It's important that we minimize or cut down these losses through the use of green urea and then NPower treated urea. So for green urea, we've seen it is very effective in reducing the volatilization losses on average by 66%. That's between 48 and 83% reduction in losses. And then for NPower, very effective in reducing N2O emissions. So on average, 68%, or between 64 and 73% reduction. So these values, like I mentioned before, they look small, like the absolute values of N2O loss at 0.2 4% on average, but its impact on the environment is huge. Like I was saying, you need almost 50 kilograms of CO2 or carbon dioxide to match this small quantities of N2 in terms of its impact on global warming. So this is a good reminder that we need to cut down losses when it comes to volatilization, ammonia volatilization, and also nitrous oxide emissions. And we have the products for that. So green urea for ammonia, and then N-power treated urea for nitrous oxide, cutting down losses from nitrous oxide emissions. So what are the implications? Losing 20 to 25% of your applied nitrogen is very significant. You are not just losing the nitrogen, but you're also losing the benefit of not applying that nitrogen. We've seen that using green urea instead of standard or untreated urea, we are able to cut down these losses by between 48 to 83% over the 16 days period that we did a measurement. So how do you do that? So we use green urea, and then the return on investment is justified. For N-power, we only lost 0.2 to 0.3%, but the impact on the environment is so huge that it can be ignored. And using N-power significantly reduced these emissions by 64 to 73%. Though the return on investment wasn't justified in this particular trial, under situations where you have a lot of soil moisture or high rainfall, this loss, the use of N-power is significantly important in terms of cutting down these losses. So where you have high soil pH, high soil moisture content, or soil waterlogging conditions, this product is very important to use. Before I get to the end, I'll just show you some of the trials. I'm sure some of you on this call are involved in this trial, but we've been doing this trial for a long time. So starting with 2024, so we did this trial across 19 different locations, including the Greenfield site. So we're measuring ammonia losses and also sometimes measuring greenhouse gas or nitrous oxide emissions. So we are continuing to do more trials in this area. So in 2025, we have around 10 sites that we are doing these trials on. So still looking at ammonia volatilization and nitrous oxide emission using green urea and N-power. So their efficacy has been justified, but I want to try it in more locations, looking at different cropping segment, different soil properties and environmental conditions. So this is ongoing, and then from time to time, we'll keep you up to date on the progress. We have some resources on our website. So if you head to the Incitec Pivot website, we have some resources. These are on green urea, but once you go to the site, we have resources on N-power and also on other products. So thank you. And then we are now in Q&A. So I'll hand over to you, Justin.
Thanks, Robert. And thanks, Jen. Some great data there. Yeah, I think, as mentioned, there's a Q&A at the top there. You can click on that and type in some questions if you've got any. I'll just double check in the chat as well, if that's an option. But please, yeah, while you've got everyone here, feel free to ask some questions. Oh, here we go. Just refreshed. I'll let Robert or Jan decide who to start with this one, but Ian Todd just asked a question on what depth is the N level measured?
The N level?
The N level, yeah. What depth, soil depth is it measured at? Is it 0 to 10, 10, 30?
It's talking about the initial soil properties.
Yes.
I think it's, yeah, for that is between, I think 0 to 15.
And so does it go any deeper, or is that it?
Yeah, the nitrogen level was measured through to 0 to 60.
60, yeah, 0 to 60. Right, yeah. I got a thumbs up there, so I think that's a good thing. There's must be a new aggro here, Charlie Walker. Any thoughts on what the ration of N2 to N2O might be at the Grenfell site?
I think he means ratio.
Yeah, he must mean ratio. It's true.
So can you repeat the question?
Any thoughts on what the ratio of N2 to N2O might be at the Grenfell site?
So yeah, we don't have the absolute, or we don't have the actual figure, but normally once you're losing N2O, you are most likely to lose more N2. So it's likely that though you are losing just 0.2 to 0.3% as N2O, in terms of N2, it could be way higher than that, but yeah, we don't have the absolute values. It can be very high. It can sometimes be even up to 30, 1 to 30 in favor of N2. So it can be very significant for N2. It wasn't measured for this side.
Thank you. Question from Charlie Mitten, Baker Ag. What is the expected losses when spreading urea onto moist ground and heavy dews, no rainfall? So gone out, spread urea on the paddock, no rain. I suppose that kind of depends on time, doesn't it? So you got to maybe just make an assumption on time, but unless you want to pop that in there, Charlie, just because that'll depend on the timeline. But yeah, what's the expected losses on urea spread with heavy dews, but no rain? Yeah, it's a bit of a tricky one.
Yeah, I think if you've got heavy dews, you've probably got enough moisture in the system. The numbers that you'll see quoted are that your potential losses are anywhere between 5 and 30%, depending on a whole lot of factors to do with your paddock, the time of year, the temperature, the pH, all sorts of things, but it can be very high.
Yeah. And just to add to that, so once you have moisture from the dew, so once you have the urea in contact with the moisture, you initiate the hydrolysis process. So like we mentioned before, the urease enzyme is everywhere. So if you are wondering, if you are wondering whether or not, you have urease enzyme in your soil, you certainly have it. So because they are everywhere. So once the urea comes in contact with moisture, you initiate the hydrolysis process. And that, depending on the conditions, yes, you can lose up to 30% or even higher through ammonia volatilization of your applied nitrogen.
Excellent, thank you. I have to start screening these internal questions. Phil Holt, how do customers with existing straight urea contracts convert them to green urea? Don't know if Jan or Rob would answer that. That's probably my question, Rob. Phil. So that's done, Phil Holt, through contacting your local regional business manager, and they can convert that over. Or you can place the order for green urea and customer service can manage it, but probably for speed and efficiency, it's just better to let your local RBM know your urea contract number and tell them how many tonnes you want to switch over to green urea, and they can add that to your contract as a separate line for ordering. So there you go. And then Graham Page, great research, thank you. Is there a decision support tool available to help advisors and farmers to make application decisions taking into consideration environmental, chemical, and economics? Did you want to answer that one about the decision tool that we've got?
Yeah, so we have a thing called the green urea calculator, very imaginatively named, but that is a tool that will help you do that, Graham. You can run some numbers through that, similar to what I've done, and it'll give you that sort of help in making those decisions. We are working on a version, an NPower version. It's not quite ready yet, but the green urea calculator is available.
Okay. Thanks for the question so far. Any, am I missing any? They tend to drop off.
There's one here that said, have any trials been done in far north Queensland, or are there any plans to? There is some work being done in the sugar region with our agronomist Rob Dwyer. It's a slightly different trial setup, but that work is ongoing at the moment. So we should be able to have a similar sort of webinar for the sugar region.
It's just worth mentioning sugar's a bit tricky with green urea as well, isn't it? Just with the trash blanket, because of the amount of trash on the soil, green urea isn't really, we don't recommend it too much, I suppose, it's better for bare soil or away from so much.
Yeah.
But have a chat to Rob about that as well.
We also,
Phil,
we also have results coming through from a trial at our long-term site at Colonsay, which is on the Darling Downs, and we have maize results from the MIA that we hope to be presenting in the near future.
Bill Holt again. What is the influence of windy conditions on losses, and does canopy biomass have an impact?
Yeah, so once you have windy condition, it's kind of makes the losses worse. So if you compare two situations where one have windy conditions, the losses there are higher than where you don't have windy conditions. So yes, for canopy, same situation. Once you have canopy, kind of minimize the losses a bit compared to where you have bare soil. But irrespective of these conditions, the losses from applying urea and being lost as ammonia are significant. So whether bare or not, still recommend the use of green urea to cut down those losses.
Robert, there's one from the chat that says, the nitrogen that is not lost, where does it go?
So once you apply the urea, and it comes in contact with moisture, the urease enzyme is there, so it's hydrolyzed to ammonium. Now that ammonium, depending on the condition, let's say high soil pH, it can be lost as part of it can be lost. So in this case, around 25% for the Grenfell trial can be lost as ammonia. Now the remaining ammonium can be converted through microbial processes to oxidized forms of nitrogen, so nitrate. Part of that nitrate can be leached, and then the rest stays. Now, whatever is not lost, some can be taken up by the plant, depending on what the plant needs for its cycle, and then part remains in the soil. Some can also be taken up by microbes and all that. So all these processes are happening around the same time. So it's not like one after the other. So you lose some, the plants take up some remain in the soil, some can be leached, but we don't want to lose it in terms of whether as gas or being leached. So that's why you want to cut down the emissions. So even if the plant is not using it, stays in your soil, you have it. So you apply green urea to cut down volatilization. You apply N-power treated urea to cut down nitrous oxide or leaching losses. Hope I've answered the question.
Okay. Excuse me. There's just another question here from Grace. Great data, thanks. It seems like there's no rainfall data included in the trial report or the results, unless I missed it. Would this be the number one consideration when considering losses?
Yeah,
there's two questions there, I suppose. Is there do we have the rainfall data for the trial site or for the trial? Yes. And then that's a number one. The question is, would it be the number one consideration when considering losses?
Yeah, so we have the rainfall data. It's not shown here. And for what I say is the number one consideration. It's one of the key considerations. So if you need a moisture, of course, to get a urea hydrolyzed and all that. And if you don't have enough rainfall to kind of push down or wash down the applied urea, the losses are high. but you also don't want to have too much rainfall. But in addition to rainfall, other factors such as the soil pH, if the pH is high, the losses are likely to be higher. If the soil has low cation exchange capacity, the losses are also likely to be higher. So yeah, the rainfall is key. Other parameters are also key. And then we have the rainfall data for this site, just as it's not shown here.
Okay, I'll just go back to Q&A and hit the refresh button. Nothing. Am I missing anything after Holty's message, Jan, or is that it? I don't think so. No. And nothing else in the Q&A.
No.
All right. Any last questions before we?
Yeah, there's just one that's just popped in.
Oh yeah, price differential versus standard urea. Who wants to answer that one? Who's in the data? I'll probably get it wrong. Is it 48? I should know. I think it's around $50, give or take. Depends who you talk to, maybe.
Yeah, so in terms of green urea, it's about $53 a tonne, I think, Justin.
Yeah,
and
it's around that
about 115 for NPAL.
That's right. Yeah, just on the urea component. That's right. But it's obviously that's our price. But yeah, I suppose it's up to our customers on how they price it to the growers as well. Oh, hang on, I might have a new one. Bill Holt, losses exacerbated in higher pH soils. Higher pH soils, Robert. So does that influence the loss mechanisms?
Yes. So once you have high soil pH, so the urea is converted to ammonium. So the ammonium is positively charged. So it can be lost through volatilization, and it's most often held on the exchange sites in the soil. Once you have high soil pH, some of or part of that ammonium can be converted to ammonia. That ammonia doesn't have a charge and it can be lost through gas. So once your soil pH is high, or the conditions created there show high soil pH, your losses are also higher.
Going once, going twice.
Going 3 times. I think Holty's reached his limit on questions. Alrighty, no problems. Right, well, we'll close out the session if that's okay. Obviously, I think most people on this call would have contacts with Incitec Pivot, and you know, we're available for any further questions that you might have. Robert and Jan, and we've got our local agronomists out there in the field, and obviously our regional business managers too. So, yeah, by all means, please reach out if you've got anything further. I think it's great from a personal note to be able to put forward this data to our customers to then, you know, go and have conversations, you know, some really well-educated and I think with some great data to back up those conversations as well with growers about how you use nitrogen in the paddock and what you should expect under different situations as well. So, and the fact that we're quite open with, you know, we think NPower has a place in the market, but we think green urea has a place in the market as well. And each, you know, I think that's why you need to have a bit of a education behind what product you're recommending. So this data certainly helps with that. Thanks, Jan, and thanks, Robert, and the agronomy team for putting that forward. And thanks everyone for dialing in this morning. I hope you got something out of it. And yeah, I'll leave you to your Friday. Have a good weekend and stay warm. Thank you.
Thanks.
Thanks, everyone.
Thank you. Bye.